Okay, so this is 15.8, which is a Stokes theorem, which is like the highlight of this course, Stokes theorem. So Stokes theorem is the higher dimensional analog of Green's theorem. So here's a statement. It says let S be an oriented surface, so we need an orientable surface to begin with. So this rules out the Mobius strip. So let S be an oriented surface with unit normal vector n bounded by a smooth simple closed curve C with a positive orientation. So I'll talk about what this means in a second. So if F is a vector field whose component functions have continuous first partial derivatives, then, so here's the statement here. So the line integral around the boundary of our surface equals the flux of the curl over the surface S. Okay, so let me explain this a bit more about what positive orientation is. Okay, so say the bowl here is our surface. So then the boundary, what we're talking about in Stokes theorem, the C, would be this guy here. That would be the boundary. So that would be the C guy right here. The S would be the bowl up here. Okay, now let's talk about the positive orientation. So I can choose the normal vector to be sticking out of the bowl, say here. So I've oriented the surface. Okay, now when it says positive orientation, I was talking about the curve C, so let's talk about that. Okay, so suppose this is you here. I've marked your hand with a black mark, okay, to keep track of it. Now I'm going to bring my bowl back over and I'm going to put you on the boundary, so the C. So you're standing on the boundary and your head's pointing in the direction of the normal vector. So in this case it is. Now when you walk around the bowl, so say you're going this way, the normal vectors should be on your left side. That'd be positive orientation. So you can see as she's walking around, the normal vectors are on the left side. So if she changes directions, but now the normal vectors would be on the right side if she walked this way. That would not be positive orientation. So the relative to this normal vector then, the positive orientation would be going this way around the bowl. So it's the normal vector is on left side as you walk around with your head in the direction of the normal vector. So in this case, that would be the going like this around the boundary would be positive orientation. Okay. So on the left side here, you can interpret this as like work done by F going around the boundary. So here in this example, again the boundary is here. So you're doing looking at the work going around the boundary. And the second, on this side we have a double integral. So this is the flux of the curl across S. So you're relating this side you have a flux, and this side you can think of as like a work. And the fact that they're equal is kind of interesting. But if you think how if you look back how the curl is defined, it does have there's derivatives involved in the curl here. So you can think of, actually if you do look at a proof of this, we will look at a proof of a special case of it in another video. But you know, when you integrate a derivative, it undoes it. So you can see that since the curl has some derivatives in it, that maybe if you could integrate one of them, it would undo the derivative. So you can see it might equal perhaps. And actually, that is in fact what's going on here. When you do look at the proof, the fundamental theorem of calculus will be used to make this double integral into one integral to make the two sides equal. That's the idea anyway. I think I'll leave it there in this video. Just a brief introduction of Stokes' theorem. We'll look at some examples in some other videos. Okay, so let's leave it there.